In the previous segment, I described how you can use an event-driven approach to maintain data consistency in a microservice architecture. And I outlined a couple of strategies for reliably publishing events whenever state changes. In other words, whenever the database gets updated. So in this section, I'm going to describe a third approach, which is sort of radically different than the previous two. And at some level, previously I described the problem of you having to atomically update the database and publish an event. And the way event sourcing can sort of be considered to work is that it actually gets rid of updating the database, and you effectively do everything using events, which sounds kind of intriguing. So the big idea is for each business entity in your system, or in domain-driven design terms, an aggregate, you identify all of the state-changing domain events. So remember, an event is something notable that happens. So you actually, as part of your modeling process, actually identify all of these domain events, and you explicitly represent them in your domain model as classes. So we will have events classes as part of our design. So if it's a shopping cart, it's order added. Sorry, if it's a shopping cart, it's item added, item removed, order placed. If it's an order, there would be various events corresponding to the life cycle of that order. Order created, cancelled, approved, rejected, shipped, etc. So that in itself is nothing profound. We're just explicitly modeling events in our domain model as first-class citizens. But where it gets exciting and different is how we actually persist our business entities. So if you think about the standard approach, is we store the current state. So for an order, that means that we would have an order table, and we would have a row in the order table that stores the current state of that order. So we'd have an ID column and a state column and so on. But with event sourcing, we don't do that. We do not store current state. And instead what we do is store the sequence of state-changing events. So at least conceptually, you can think that there's an event table that for every entity, there are one or more events of certain types which have some data. Simply speaking, you could think of the data as sort of a JSON blob. So when an order gets created, we insert an order created event. Later on, when the order gets approved, because the credit check succeeded, we have an order approved event. And then maybe right after that, or sometime later, we have the order shipped event. Maybe there's like credit or the customer billed event, something like that. So we actually store a sequence of state-changing events for every business entity or aggregate in our system. But of course, in order to write any business logic, we tend to need the current state of a business entity, but we actually recreate the current state by replaying events. So we'd load all of the orders events and just replay them, reconstruct the current state. And that works perfectly for objects like orders that have a relatively limited lifetime. Now you might be wondering, say with an account, like a bank account that you could have open for many years, that would be a humongous number of debits and credits. And loading them and replaying 10 years worth of account history would be expensive. And so what you can do is periodically take snapshots of the current state and then find the most recent snapshot and then the events that have occurred since then, and then replay them to reconstruct the current state. So you actually don't have to go back to the beginning of time and reconstruct and replay everything. So it covers both objects that have a limited life cycle plus very long-lived objects. And if you're functionally oriented, you could actually think of computing the present state of an object as doing a functional fold over the history of the object. But that's just sort of a functional programming joke. So these aggregates or business entities, you can actually think of them as doing two things. First, they consume commands and emit events. So a command comes in like create an order or reserve credit, and events come out like order created, credit reserved, credit check failed event. You can also think of aggregates as consuming events and updating their state. So in a functional language where you have immutable objects, that this is done functionally, and an event plus an aggregate gives you an updated copy of that aggregate, whereas in a more traditional language, that would just do an in-place update. Well, two things: commands in, events out, events in, updated state out. That's kind of the two abstract ways of viewing business entities in the system. Then the way that requests are handled look like this. So say a request comes in to update an order. The order service would go find the events for that order. It would load them from the event store, the store of events. It would then instantiate an order using its, say, default constructor, so a blank one. It would then reconstruct the current state by replaying those events. So now we've reconstituted our order. We tell the order to process the command. So that's from the HTTP request. That gives us new events. We then apply those events, which gives us the updated state, which we could generate JSON or HTML from, whatever makes sense for the request handling. And then we save the events, the new events, back in the event store. So that's a very event-centric way of actually processing events. And we could actually use optimistic locking when we save events to verify that between the find and the save, that aggregate has not actually been updated. And if it had been, we could just catch the optimistic locking exception, loop, and retry. So that's an event-centric way of representing entities and persisting them in the database. But the other aspect that sort of makes it really exciting and relevant is that other services can then subscribe to those events. So in this case, the customer service can say, whenever there's an order created event, let me know. Then when one of those events get published, the customer service can then turn around and update the corresponding customer. So that's one common scenario. And that is how we would implement that eventually consistent transaction that performs the credit check. So in this case, an order gets created. We actually go and do a credit check for that customer, which then publishes another event that gets consumed by the order service. Other services can then can also subscribe, but rather than update business entities, they can do other things. They could, for example, update a materialized view of the data. And I'm going to talk more about that later. Or perhaps they could send out notifications. You could have an event subscriber that, when an order gets approved, sends out an email. Or perhaps it sends out a text message via Twilio. There's no end of the different kinds of things that you could do. So I want to talk briefly about the event store. One way of considering the event store is that it's basically a hybrid database and a message broker. So it has an API for saving events and appending events, and also an API for getting events. So that's very, very database-like. But then it also has an API for subscribing to events and notifying subscribers. And you can think of that as a sort of message broker type capability. So various different ways of implementing the event store. A lot of people just build their own. For instance, I talked recently with someone who was using Postgres as the event store, and the subscription mechanism was based on Atom feeds that were generated from data that was stored in Postgres. Greg Young, who's off in .NET land, has a open source project and a product called Event Store that provides this functionality. And this is exactly what my startup Eventuate is working on as well. So there are various benefits to using event sourcing. So number one, it enables you to implement an event-driven architecture that solves the data consistency issues that arise in a microservice architecture or a polyglot persistence architecture where you have lots of databases that need to be consistent. It has a reliable event publishing mechanism, so if you need events to flow into your predictive analytics machine learning engine, it can do that. If you need events to send out emails and SMSs to users, it can do that too. It mostly eliminates the OR mapping problem, which is great, because what's getting persisted are events, which tend to have a simple structure and they can be easily serialized. Also, because you've turned events into long-lived data, the fancy word for that is you've reified the state changes. There's a couple of really, really interesting benefits. Number one, you actually get a built-in reliable audit log. Because every state change corresponds to an event, you are guaranteed that whenever someone changes something, you will get a record of it, right? Which is quite different from a conventional way of implementing audit logging where you have to remember to write the code to insert data into an audit logging table, for example, which is error prone and not guaranteed. Also, because you've got the entire history of an object as a sequence of events, you can actually ask questions. What was the state of this object a week ago? And you can replay events just to that point, and you have the current state, which lets you perform temporal queries. Another really interesting aspect to the system is that you have preserved the history of everything that has happened inside the system. So this means that you could implement a feature today, replay past events through this new component, and it would be as if you had implemented that component sometime in the past, as opposed to implementing it today and it will only know about things going forward. Now it can actually know about things that have happened in the past, which is somewhat of an intriguing idea. So there are some drawbacks, of course, right? So, number one, it requires a rewrite of your application. Your business logic is written in a quite different way. But if you think about the move to microservices, that's actually requiring an application rewrite. So that would be a great time to actually adopt an event sourcing model because it solves the problems with microservices and it gives you all these extra benefits as well. It's also a different way of writing your code. So it's sort of weird and there's a learning curve. But it's not actually that big. You get used to it quite quickly. Another problem is events end up being a historical record of all of your design decisions, both good and bad. Events never go away. So unlike making a mistake with a database schema that you can apply migrations to make it go away, with events you tend to have to live with them forever. But usually I think in practice it's not that bad events tend to be very much in the problem domain as opposed to being developer creations, and so they're fairly simple and fairly stable. You do need to implement a mechanism to detect and ignore duplicate events, right? That, this is a message-based system, and so most message-based systems guarantee at least once message delivery, which means that you have to be prepared to handle duplicates. Sometimes your event handlers can just be idempotent. They can be executed any number of times, and so they will just naturally ignore duplicate events. Or you would have to do things like keep track of the most recently seen event ID and then just ignore older ones. So it's some work, but it's usually quite straightforward to solve. And then lastly, another interesting problem is executing queries. So querying the event store can be challenging because you don't actually have the current state. So if you want to write a query that's about the current state, your SQL, say, would actually have to reconstruct the current state from the events that it finds in the database, which could mean that you write some quite complex, possibly inefficient queries. And that's assuming that you're running on top of a database running on top of a SQL database. You might actually be using a NoSQL database that basically only lets you retrieve events by event type, by entity ID, in which case you can only directly support a very, very limited range of queries, which can be problematic. And the general solution to this is use an approach known as command query responsibility segregation, or CQRS, which is where by subscribing to event streams, you maintain these denormalized views of the data that you can then query easily. So there's a whole lot of complexity around it, but because you got this stream of events, maintaining views ends up being quite straightforward. The big idea with event sourcing is that you persist entities by storing the sequence of state-changing events and then reconstructing current state by replaying them. And that ends up with a whole host of benefits. It basically means that saving an update translates into saving a new event, which can then get published out to other interested parties in the system. And it's a great way of implementing an event-driven architecture.